Hello everyone. So today we're going to start on the Fundamental Theorem of Calculus Part 1. So just to let you know, this is fundamental. Okay, so today, actually on Friday, I gave you kind of a Cliff Notes version of the Fundamental Theorem of Calculus. And in general, using it is really simple. So just to kind of go back, if you are to have that a function capital F prime of x is equal to a little f of x. So that is, capital F of x is the antiderivative, or is let's erase that. It just has to be is an antiderivative of little f of x, then the integral from a to b of little f of x, which is the derivative of capital F of x, is f of b minus f of a. So in practice, if we have from 1 to 3 of x over 4 dx, then we just need to take an antiderivative. So that's going to be x squared over 8 from 1 to 3. And you just need to plug those in. So it's going to be 3 squared over 8 minus 1 squared over 8, which is 1. Oh, that's interesting. Because it's 9/8 minus 1/8. So it's 8/8, which is 1. But anyway, in practice, it's fairly straightforward. And then just because I think a few of you might have gotten lost here, I added 1 to the power of x, which is squared, and then you have to divide by that new power. And so this 4 is on the bottom, so when you divide by 2, you're multiplying this 1/4 by 2 to get 1/8. So let's look at the Fundamental Theorem of Calculus in practice. So the weatherman predicted that the rate of snow accumulation for the next 4 hours can be given by f of t is equal to negative t squared plus 4t inches per hour at time t. So what I want you to notice is this word rate. So the rate is given by this function. So if the rate is given by this function, then this function is a rate. And indeed, we're going to make a note here, f of t is a rate, which means f of t is a derivative. All right, let's zoom out a little bit. So if f of t is a rate and f of t is a derivative, what is it a derivative of? So what is f of t a derivative of? I know that's not proper grammar, but let's just keep on going. So if f of t is a derivative and its units are inches per hour and it's of snow accumulation, then little f of t is going to be the derivative of the amount of snow on the ground. Okay, and so let's say that that is A of t. So the amount of snow on the ground at time t. Okay, always be looking, especially within word problems, see if you're given a rate or a velocity or something along those lines. And then think, what is it a rate of? What is it keeping track of? What is changing over time? So here, kind of the hint is the rate of snow accumulation. So we know it's an amount of snow. And then on top of that, look at the units. Remember, a rate is always something usually over time. And so the thing it's going to be taking a derivative of will have the units of inches. And so the amount of snow on the ground does have units of inches. And so let's ask a question. So I'm going to ask the first question. So part A is, and I'm going to zoom, or actually no. What is the total change in the height of snow from hour 1 to hour, let's go with 3.5. So what's that total change? So if we think about it, if we have the height of the snow at 3.5, we can subtract the height of the snow at 1. But remember, the derivative of this guy is f of t. So this means that you just need to take the antiderivative or an antiderivative of f of t in order to do this. So this is the same thing as the integral from 1 to 3.5 of f of t dt. Because a of t is the antiderivative of f of t. And so when you do this, this is going to be the integral of negative t squared plus 4t dt from 1 to 3.5. All right? Which is equal to, take that antiderivative, so we go up in a power, so that's going to be negative t cubed over 3, plus, and then you go up in a power for t, so that becomes t squared, and then 4 over 2. And we want to check out the change from this. So remember, this thing is an antiderivative, so this is a of t. All right? And then you plug them in, and you have 3.5 cubed, or negative 3.5 cubed over 3, plus 2 times 3.5 squared, minus, and now you have 1, so negative 1 cubed over 3, plus 2 times 1 squared, which is approximately 8.5417. So just going back, we were given a rate of change, and we were asked for a total change. And so with that rate of change, we found the antiderivative, and we wanted to know the total change of the antiderivative. And so to find that total change, you just need to find the antiderivative. So the antiderivative of f of t is this negative t cubed over 3 plus 2t squared. And then you need to take that difference. So plug in 3.5 and plug in 1 and take the difference. And so, like, Fundamental Theorem of Calculus, really nice stuff. It's very, very useful. Now, I'm going to erase this part A and all this work we just did, and I'm going to write a part B on the same page. And so, press pause. So, suppose that there were already 5 inches of snow on the ground when this all started. What function gives you or gives the amount of snow at time x? Okay, so we already know that the amount of snow is going to be this antiderivative, right? We already know it's going to be an antiderivative. So if we were to find the antiderivative of this guy, which we've already done, then the antiderivative of f of t, which is, the antiderivative of negative t squared plus 4t dt, is going to be negative t cubed over 3 plus 2t squared plus c. Now remember, we have this constant because when you take the derivative of c of a constant, then it's just 0. And so you're back to this being your derivative, okay? So what's important as we look at this, Suppose that there were already 5 inches of snow on the ground when this all started. So that means at time 0, that is t equals 0, a of 0 equals 5. And so this right here, this is our a of t, right? So a of t is this buddy. So a of 0 is equal to 5, which is equal to negative 0 cubed over 3 plus 2 times 0 squared plus c, which gives us that c is equal to 5. All right, so our function that gives the amount of snow on the ground when it starts with 5 inches is going to be this antiderivative with c equal to 5. So we have negative x cubed over 3 plus 2x squared plus 5. Now you might be wondering, why did I change the variable? Now in this problem, it doesn't make a lot of sense. It would have just been fine to keep the t, but this is actually an example of the Fundamental Theorem of Calculus Part 2. And so what we can do is we could write what we just did as the antiderivative from time 0 to time x of this negative t squared plus 4t dt. And when you do that, you're going to end up with x here. And again, actually, I don't think I did a really good job of explaining that. But anyway, let me try again. These t's go with this dt. So this t is running from 0 to whatever x may be, whatever your limit of integration may be. And then x is where you're checking the amount of snow. So t is running over that rate of change, and x is where you stop. And so we are just replacing your ending value with a variable, your ending limit of integration with a variable, so that you can adjust where your b is. We'll go more into depth on the Fundamental Theorem of Calculus Part 2, probably either Wednesday or Friday. Just real quick, I believe Thursday is another quiz. So now let's discuss why the Fundamental Theorem of Calculus Part 1 works. And so just to kind of remind you, we had this triangle where we were looking at antiderivatives, area by slices, and rate of change giving total change. The Fundamental Theorem of Calculus is this part right here. It's where you're given a rate of change, you're given a derivative, and you had to find the total change of the antiderivative. But in order to use this, you need to use antiderivatives to find that function to get the total change. We can also explore the idea as area as well under a curve. And so all of this is linked together underneath the Fundamental Theorem of Calculus. And indeed, from now on, I will call this bubble the Fundamental Theorem of Calculus, because it is the rate of change gives a total change. So why does this work? So number one, I'm going to say it works because common sense. All right, if you are given a rate of change, you find out what it's a rate of change of, and then you take the total change. You take the difference of your original function. So given a rate of change of a function, you just need to find the original function or the antiderivative of your rate of change. So this is the antiderivative of your rate of change. And take the difference to find a total change. Okay, so that is why it makes sense. It's common sense. Maybe not common sense, but logical sense. But let's look at it in terms of like maybe more of this area idea. And so I'm going to go up here and I'm going to draw a picture. So let's say that you have, so this is number 2. This is the second way to think of it. You have from A to B, and then some function right here, which we're going to call f prime of x. All right, so this is our derivative or our rate of change. Our rate of change graphed on here. And we want to find what is the total change from B to A. The total change from B to A. Then what we can do is let's think about this as those rectangles where you're finding the area under the curve. And so if we were to like just make a whole bunch of these really skinny rectangles, and then we're just going to look at one right here. Okay? Then remember, I'm going to call this df dx because it's the change in f over the change in x. Remember? For the rate of change. And then we're going to say the width here is our change in x. So that's our delta x. So if you think back to how we set up our Riemann sums, it's delta x, which we're going to represent with the dx. So this really, really thin rectangle has a width of dx and a height of df dx, right? So to get the area of a single rectangle, you're going to have df dx, which is your height, times your width dx, which comes out as df, right? So you're kind of getting these dx's canceled, which is a small change in f. So df is a small change in f. So to get a total change in f, so a total change in f, add up all the little changes. So add up all the little changes, df. Okay? All right? So if we wanted to do that, let's write this as a sum. And so we would have the sum of all these, so a total change, so f of b minus f of a, so a total change in f is going to be the sum of all these df's, okay? Which we already said the df's are the sum of df dx times dx, which is the same thing as the sum of those little f prime of x. And I'm going to actually change this a little bit. We're going to say that this is of f prime of x sub j times, and instead of dx, we're going to say delta x of j. And if you look at this, this is a Riemann sum. I know I've been ignoring like the stuff that goes on the summation. I hope you guys realize this, which is going to be that letting j, so if we let that j go to infinity, so limit as j goes to infinity, so let the number of rectangles go to infinity. Oh, let me change not j to n. So erase. This should be an n. So if we let the number of rectangles go to infinity from j equals 1 of f prime of xj times delta xj, then remember this is the antiderivative from a to b of f prime of x dx. All right? So just in general, like, you can explore this idea in terms of area. Okay? Cool. So looking back at this, to get the area under the curve of f prime of x from a to b is the same thing as finding the antiderivative and just taking the total change, which means that from now on, if you ever need to find an area under the curve, you can just use the fundamental theorem of calculus. Cool. All right, so to use the fundamental theorem of calculus, pretty straightforward. And so let's just do some examples. So that first example is the integral from 1 to 2 of x squared minus 3 dx. So we want to start by taking an antiderivative. So the antiderivative of x squared is, we go up in power with the 3, and then times 1/3, minus, and then the antiderivative of 3 is 3x. Oops. So that, and we're going to, okay, whatever. So 1 to 2. Some of you might be wondering, okay, why don't we ever add on a constant? Like, why don't we put plus 2 in our antiderivative? You are allowed to do that. If you put in a plus 2 at the end here, when you take that difference and you subtract, you're going to have a plus 2 up here minus a plus 2 over here, and that plus 2 will cancel. So you might as well pick your constant to be 0. But anyway, let's plug in these. So we've got 1/3 times 2 cubed minus 3 times 2 minus, and then use those parentheses, 1/3 times 1 cubed minus 3 times 1, which is equal to negative 2/3, I believe. So I did that kind of quickly, so I might have gotten my arithmetic wrong, but anyway, you just figure out what this is. Now let's go on and do the next guy. So we have the definite integral from 1 to e of 7 over u du. So this is just saying this is acting like our x. You can use any variable here. And so this is the same thing as 7 times the integral from 1 to e of 1 over u du. So you are allowed to pull out those constants. Or you could just remember that you can treat it like a constant. And that 1 over u is natural log. The antiderivative of that is natural log. So you get 7 times the natural log of the absolute value of u from 1 to e. And so that's going to be 7 natural log of e minus 7 natural log of 1, which is, all right, so 7 natural log of e, so that's asking what power of e gives you e, so that's 1, minus 7 times what power of e gives you 1, which is 0. So it just comes out to being 7. All right. Now let's look at this last example. So we've got the antiderivative from pi over 2 to pi of sine of 2 theta d theta. And so to take the antiderivative here, the antiderivative of sine is negative cosine. So it's going to be cosine of 2 theta with a negative, but because we have this 2 here, it's going to be 1/2. And so we got negative from the sine to cosine, but over 1/2 from that 2 on the inside. And we are going from pi over 2 to pi. So when you plug that in, you have negative 1/2 cosine of 2 times pi minus negative 1/2 cosine of 2 times pi over 2, which is pi, which comes out to be, let's see here, so cosine of 2 pi is 1, and so that's negative 1/2 times 1, and then minus, so that's plus, and then cosine of pi is negative 1, so it just comes out to being negative 1/2 minus 1/2, which is a total of negative 1. So just looking at these, this is using the Fundamental Theorem of Calculus, Part 1, just its common usage. So like if you're looking through this and yeah, Fundamental Theorem of Calculus is your friend. Using it is awesome. So this was Friday's You Do question, and we were asked, or I asked you guys, to find this limit. So this was a Riemann sum definition of the integral, and I told you to rewrite this part so that it matches this part to start. And so if you were to do that, what you should end up with is it's minus, erase that. So if you were to rewrite that, instead of a plus, you'd have minus, and then this is twice that. So it's minus 2 times that negative 3 plus 5j over n, all right? And so when you set this up as an integral using the fundamental theorem of calculus, then if we look at this, the width, I think there was an issue here. So our original problem, for it to work, you'd need that whole width times everything. So I think I forgot a set of parentheses. So if you're going through and you saw that, that is the change that needed to be done. But anyway, you have that the width of an individual rectangle is 5 over n. So the width of the entire length is 5. And then if you look at this guy, you're starting at negative 3. And so if you were to write in your limits of integration, you start at negative 3 and you go up by 5. And so from negative 3 to 2, you end up with this. And then you're replacing, let's go back, undo. So you're replacing the negative 3 plus 5j over n, that is your x. So your inside function here is going to be x squared minus 2x dx. And so if you wanted to solve this with the fundamental theorem of calculus, you could do that very, very easily. So the antiderivative of x squared is x cubed over 3 minus, and then the antiderivative of negative 2x is x squared. And you're going from negative 3 to 2. So you plug those in, and you have negative 3 all cubed over 3 minus negative 3 squared minus 2 cubed over 3 minus 2 squared, which is negative 32 thirds. So that's what the fundamental theorem of calculus all worked out. But let's do this, but instead with the power sums. And so we're going to set this up. So the limit as n goes to infinity, and you know what, I'm going to zoom in so I just have a little bit more room here. So the limit as n goes to infinity, we're going to pull out that 5 over n. We're going to distribute this squared. So we're going to have the sum from j equals 1 to n of 9 minus 30 over nj plus 25 over n squared j squared. So that is just this squared out, plus, or actually minus, and then 2, and then you have this minus 3 plus 5j over n from j equals 1 to n. Okay, so this is what we're working with. Just kind of all over the place. And then let's distribute this. So we get the limit as n goes to infinity of 5 over n of, let's combine like terms. I'm going to just rewrite this, so press pause, it's going to be nice. So I distributed and combined like terms, so this 9 and then plus this negative 3 times this negative 2 to get plus 6, so that's 15. And then I combined this term with this term, but this was actually 5j over n times negative 2. So that's minus 10j over n, which gives us negative 40j. And now I'm going to separate it out. And then I'm going to apply the power sums to the 15, the j, and the j squared. So here are the power sums. So the sum of 15 up to n is 15n. With the j, you have n squared plus n over 2. And with j squared, you have 2n cubed plus 3n squared plus n over 6. And then I'm going to distribute this and put them in individual terms. So when these are distributed into individual terms, then we end up with 1 guy, 2, and 3, where you have n over n squared over n squared, and n cubed over n cubed. Now remember, all of this, n over n is 1, n squared over n squared is 1, and n cubed over n cubed is 1. And all the rest, the top is growing much slower than the bottom. And so as n goes to infinity, these pieces go to 0, which means your answer is going to be, let's see here, 75 minus 100 plus 250 over 6, which is equal to 50 over 3, which these do not match, so something went wrong somewhere. So I made a mistake. Let me see if I can figure out where it's at. Okay, I found one error. So it turns out that this should be negative 44 over 3, but I am not sure what went wrong over here. So I'm going to have to look at this and see if I can get this to you guys tomorrow. Because I want to be able to upload this by the time that class starts. So let me give you today's you-do problem. So you-do. So today's you-do problem is do your homework. So there is a paper homework due tonight. So paper due tonight. And I would work on WebAssign. So a lot of this is just going to be really, really good for you to go through, especially like 5.2 and 5.3, and just start doing it and see if you understand it. Today, there is a Zoom meeting from 3:30 to 4. I will be putting the link to that up on the announcements of Canvas. And also there is a password. I don't know if you need the password if you're using the link, but it's the same password every time. It'll also be in the announcements. But otherwise than that, have a wonderful day. I am going to sit here and try to figure out what's going wrong with this. But anyway, have a wonderful day, and yeah.